All right. Hello. Good evening, everyone. Welcome to today's JUPEB math class. We are in week 7 of our mathematics lecture series, and today we are going to be continuing where we left off from last week on trigonometry. So this is part 2 of trigonometry and conic sections. So I think it would be much more helpful if you are in week 1's class, because this is a continuation. So trigonometry as a topic is quite broad and very vast. So you have to break it into 2 different parts and then have just the first part. So we had trigonometry 1 last week, week 6, and then we looked at the various concepts and relationships that had to do with trigonometry. Of course, this was together with some other topics, so that's why we couldn't finish all of it last week. So for week 7, we are going to be looking at what's left. So hence we are calling it week 2, and then we're not going to be going into conic sections as well. So that's basically our outline for today. My name is Olusegun, your tutor for today as usual, and welcome. Let's get right into it. So I hope those of you on this call can hear me. If I think I have just one person on the call, Iwuka Anthony. So please, if you can hear me, just signify maybe with an emoji reaction, or you can just unmute your mic and let me know. Anthony, if you can hear me, just kindly signify so that I know that I'm audible. Okay, I don't know if Anthony is actually on call, but anyway, I guess we'll just go ahead nonetheless. Hopefully I'm audible enough. So the class is actually worth your while. So yeah, let's get right into it. So we're looking at trigonometry, right? And we've established last week in our week 6 class what the basics of trigonometry are. So first of all, let's look at the objectives. What are we going to, what do we aim to achieve at the end of this class? So we are able to interpret sine, cosine, and tangent graphs, utilize inverse trig functions and key identities, so trigonometric identities, then derive the conic equations, so identify the standard equations for circles, parabolas, ellipses, and hyperbolas, and then be able to apply these concepts to solve geometric problems which involve conics. So this is basically what we aim to achieve by the end of this class. So yeah, without further ado, let's begin. So if you remember from last week, we talked about the basic trigonometric functions, the 3 of them, where we looked at on the Cartesian plane, where each one of them falls in, and where between what angle to what angle, which trigonometric function is positive or negative, and vice versa. So now we're going to be leveraging on that knowledge and the knowledge of sets and other topics that we've covered in these lecture series in order to look at the graphical representations of sine, cosine, and tangent functions. So for short, we're going to be just calling them sine, cos, and tan. So these are like the shorthand representations for these trigonometric functions, right? So first of all, the graph of sine x. So if you remember when we did sets, right? When we looked at sets, we mentioned that for every function, when we did domains and functions, we mentioned that for every function there is a domain and there's a range, right? So if you recall, the range is the span, so the possible output you can get from a function, right? So for example, you have a function where the only possible outcome you can get are positive numbers, right? So your range of that function will be from 0 to positive infinity, right? So this is like for whatever input you put into that function, this is the range of outputs that can come out, right? Regardless of whatever input you use. So that's just a quick reminder of what the range is when we're talking about functions. Now for the sine graph, or for the sine function, it has a range from -1 to 1 inclusive, right? So of course this bracket shows us that -1 is included. So you can have an output, an answer of -1, and then all the numbers from -1 going all the way up until 1, which is included as well, right? That's the sine function. And so the key points to note we all know when we're talking about sine trigonometric functions generally are the angles, right? So these angles here are expressed in radians. And if you remember, if you recall, we've had a lecture series in one of the topics where we looked at the conversions from radians to degrees and then the conversions back from degrees to radians. So you should be familiar with that as well by now, right? So of course here we are giving key points that are important. So these are like the turning points or the inflection points on the sine graph. We have we'll actually see a sine graph. I think we should just go into it now so it's evident what I'm talking about. So this is the graph of sine function, right? So as you can see, it's like a wave, right? It goes up and comes down and goes up and comes down and goes up and comes down. Yeah. So it's a sinusoidal. So that's where the word sinusoidal comes from, right? So when we talk about the sinusoidal wave or a sinusoidal waveform, it's because this is the sine function graphical representation. So it's taking that wave-like form, right? So it's up and down and up and down and up and down. So this is how the sine function is represented. And then if you notice, you would see that the bottom of the sine wave gets to -1. That's the lowest point. And then the top of the sine wave gets to 1. Now, this shows that our conclusion or our postulation that the range of the sine function is from -1 to 1 is actually correct, because there is no exceeding -1 towards the bottom and there is no exceeding 1 towards the top. The graph lies between -1 and 1, right? Every single point. So we have the maximum point at 1 and then the minimum point at -1. So that's the graph of the sine function. Now, another important thing to note is that the sine function passes through the origin, right? So here we have the sine function passing through the 0 point. So there's a value that you put into the sine function and you get 0 for it. Right, so the key points, like as I mentioned, are 0, pi over 2, pi. So if you remember, pi in radians is 180 degrees as well. So it's important to note that, because when you're dealing with trig functions, you can either be dealing with them in degrees or you can either be dealing with them in radians. So it's important to have a good grasp of how to do those conversions, how to be able to just see it and know. So for example, it should be common knowledge right now that pi in radians is 180, right? So if you see pi over 2, that should be 90 degrees, right? If you see 2 pi, that should be 2 times 180, that's 360 degrees. If you see 3 pi over 2, then you know that that's 270 degrees. So basically, these are the key points. Now, why did they say that these are the key points, right? Because if you look at it, now, this is the sine wave. First key point mentioned is 0. Of course, it passes to the origin. The next one is 90, right? 90 is, you trace it to the graph, it's the maximum, one of the maximum points you have on the graph. And then 180 passes through the x-axis again, and 270 is one of the minimum points, right? So below, that's like the minimum depth it gets. And then it comes back again and passes through the original, where 360 degrees is 2 pi. So you can see why these particular points have been outlined as key points in the graph, because they are, special. The graph passes region, it has a maximum. Sorry, someone's mic turned on. Kindly mute your mic. I'm getting some feedback from your end. Hello. Hello, Anthony. Please kindly mute your mic. I'm getting feedback from your end.
Okay.
Thank you very much. So that is what we need to know for the sine function, right? So basically, so then before I move on, another thing to explain is the period, right? So you can see here written that the period of the sine function is 2 pi. Now, what does that mean? Now, if you were here in the last class, you would notice when we made a point that there is a repetition when it comes to this trigonometric function, right? So now, what is the period actually? The period is the time that it takes for something to complete, to make one complete, rotation or revolution or cycle. Yeah, that's a much better word. Now, the period of the sine function is 2 pi. Why? If you look at the graph of the sine function, And first of all, 2 pi 360 degrees, right? If you look at this, the graph of the sine function, you will see that she started off from 0, and then you go to 90 to 180 to 360. Then you start from 360 again. So once you get back to 360, you are basically repeating the same movement that you repeated when you started from 0. And this is how the sine wave is, right? It is cyclic function. So it's just repeating the same function once it gets to a particular point. Now, that point to the origin is what we call the period, because it's the time it takes for it to make one complete revolution. So it goes from here, goes up, come down, and it goes back to 360, right? So in essence, that is the period of this function, because that's time that the total time it takes for it to run around and then come back to the starting point, which is here. So the period of the sine function is 2 pi, right? So now we move on to the cos function. So the cos function is almost similar to the sine function, except that there are a few varieties, a few here, right? And then we go, and then we go, and then we come back, and then we come back, and then we are here now, right? So this is the starting point, and then it's the same point at which you started up this graph, right? So it shows you that we have made one complete revolution, and now we are back to where we started from, right? So that is what is implied by period, and of course the same for the cosine and sine function. The range is also from -1 to 1, as can be seen in this graph over here. So -1 is the lowest possible they can go, and 1 is the highest possible they can go. And then the maximum is at x equals to 0. Now, what does that mean? So if you look at the graph once again, you see that the maximum point, so when they say maximum point, so the point at which the graph gets its highest possible point. So we can trace that and we see that the maximum points. And so because this graph is a cyclic graph, because it's repetitive, you will see that the same thing is repeating over and over again, and you can have multiple maximum points. But then the point is, the maximum point is the point where this function is equal to 0, right? And then, of course, key points as well are similarly like what we have in the sine function. So nothing to worry about. Then the next thing to move on to now is the tangent function, right? Now, for the tangent function, we are looking at something that is slightly different. I don't know if slightly is the right word, but then there are a few oddities and differences in the tangent function. So the first thing to note is that the period of the tangent function is 1, is pi, right? Now, converting pi to degrees is 180 degrees. So basically, it takes the tangent function 180 degrees to complete one full cycle, right? Complete one full cycle to 180 degrees. Now, another thing to note about the tangent function is that it's undefined at all the multiples of pi over 2, right? So the tangent function is pretty unique, such that there are values where there are inputs that you put the tangent function and you will not get any values for them, right? So you see something like undefined and things like that. So it is because at certain points in that tangent function, so I think I have the graph of the tangent function line somewhere. So that it's necessary to have that to be able to explain, or make my points. Just hold on, let me see if I can find it. Okay, fantastic. So this is the graph of the tangent function, right? And as you can see, it's pretty unique, right? It's very different from what we had before. But then the point I'm trying to make is that there are points where the tangent graph doesn't even touch, right? So for example, this straight vertical line that running across 90 degrees, there is nowhere in the graph that it passes through, right? So tangent function is pretty unique in that it just passes through here and then goes up, 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 never comes down. And then at some point, that graph cannot become parallel to the straight line, right? So they are never going to meet in the future, right? So this is the shape of a tangent function. There are other characteristics and factors. So let's look at them one by one. The first thing to note is that key points, right? So minus pi over 2, 0, and pi over 2, those are the ones he mentioned to me. So we can see that 0, this is where passes the origin. Pi over 2 is 90 degrees. So 90 degrees is a point where there is no actual point on the graph where it touches. So if you tried before, when you try to do tan 90 and you see on the point, now you know the reason why that your calculator should be on time, because there is nowhere on this graph that this line, this 90 or 189 or whatever, passes through, right? So hence you see that it's undefined at all multiples of them. So that's the tan function for you. Those are the graphical representations. So it's important to just know, have these things at your fingertips. So for example, you've known now today that if you see something like tan 90, there's no need to stressing yourself. It's undefined, right? You see something like cos 0 or sin 0. Based on the arrangement in this graph, you should be able to determine what that value is, right? And then these are the utility things that you should pick up from what we are learning here, so that you can now apply from this time to be able to use it. Right? So we've looked at the graphs, how they are distinct, their ranges and key points, and all of that and all of that. So those are the characteristics of the trigonometric functions, sine, cos, and tan functions. So the next thing we're going to be looking at now are the inverse trigonometric functions. Now, we've looked at the trigonometric functions and they are the normal sine this, cos this, and tan this, right? But now we have the inverse trigonometric functions. Now, when we are doing the trigonometric functions, we normally have what? Angles, right? So when we get that angle, then we solve. At that angle now is our input, then we solve and then get our answer. Now, what the inverse trigonometric functions try to do is to be able to give you that answer, right? And then you solve backwards and forth. Although most times it's not really solving. If you have a four-figure table, you can just look through and then assess it. Right. So now the inverse functions, so like I've said, you have the number and then you want to go backwards and get the degree or the angle. So basically the representation is just by adding this superscript of -1 to all of them, right? And then every other thing remains the same. So these are the inverse trigonometric functions, and then we just see a few examples of how they apply. So cos inverse of 0 is pi over 2, that's 90 degrees, right? Tan inverse of 1 is pi over 4. So here there are a few examples of using the sine inverse function. So sine inverse of 1 is pi over 2, which is 90 degrees. Cos inverse of 0. Right. So of course the inverse trigonometric function. So for trigonometric functions, it's easier to be able to access them. Of course, if you have a calculator or a four-figure table, then it's easier to just trace them out, knowing. But then with time, some of these basic ones will just come naturally to you. So for example, someone can wake me up from sleep and ask me what tan 45 is, and I know that tan 45 is 1 because I've solved a lot of examples. I've come across it many times, more often than not, and so you just know that tan 45 is 1. So things like this should be second nature, such that you're always having them at your fingertips, and then as you practice more, as you do more exercises, your brain is being exposed, you know more, you realize more, and then you're able to remember much more accurately, right? So here tan inverse of -1, tan inverse of 1 today. So those are how the trigonometric inverse functions work. So here we have an example of sine inverse of 1, which is 90 degrees, cos inverse of 0, which is also 90 degrees, and then tan inverse of 1, which is 45 degrees. Yeah, so now we're going to be looking at the trigonometric identities. Now, when we say trigonometric identities, what do we mean? So we mean that there are equations or formulas that can help us to be able to, do trigonometric functions or solve them more effectively, right? So there are a bunch of theorems, a bunch of laws and everything. So when you get the slide, it is advised that you just look through all of them and then mull over it. If possible, use some examples and then so like I said, the trigonometric identities are quite a lot. There are a plethora of them, right? So here we have an additional lineup of trigonometric identities, but then the basic ones that usually come up more often are listed out here. So we have sine squared theta plus cos squared theta is 1. 1 plus tan squared theta is sec squared theta. Now, sec is something you've not come across before, right? But then sec is actually the inverse of sine, right? So trigonometric identity, 1 plus tan squared, this is sec squared. This, like I've said, sec theta is the inverse of sine theta, right? And then we have cot. So cot is now the inverse of tan theta. And then we have cosec as well. So right, so if you look at the following table, we have a lot of trigonometric identity. So like I said, these things are just here to be able to make your solving or deduction easier, right? So for example, you want to transpose sine A plus B into here, something like this, because you feel that it's going to be easier for you to solve. Now, we don't have to try trigonometric identity. What you just need is to, say, okay, what is my A, what is my B, and then express it in this form, and then you know that you are correct, and then you start to solve, right? So most of these things are, have extensive proofs that have been done, extensive deductions to know what exactly applies and which one is for which, right? So, but then it's important to be able to, know at least the basic ones so that you can be able to apply them in your solving and your calculation. So, yeah, sum of angles for sine, sum of angles for cos, difference of angles for tan, product to sum, half angle formulas. So just make sure you take your time as thoroughly as possible. And then you can even, do checks with it. So for example, I'm telling you that sine squared theta plus cos squared theta is 1 now. Sine squared theta means you do sine theta and it's squared, right? So you can just pick 2 random angles that you know, right? And then, so for example, let's say we want to work for 60 degrees or whatever. And then we just plug in 60 degrees here, plug in 60 degrees here, and do sine squared 60 plus cos squared is 60. If this identity is correct, then your answer should be 1, which it will be, because this identity is actually correct. Then you can try the same thing for this one, and then for this one, and for this one. So, like I said, sec squared theta is inverse of what? It's inverse of sine, right? Sine, right? Or sec. Yes, sine squared theta. So it's able to, easily deduce that contangent from another blank from another, then go into looking at all of the remainder ones because they will be important subsequently, right? So for trigonometric identities, it's pretty straightforward. So it's just all about understanding the concept. I don't know whether you're planning to go to use a Formiga table. Those of you that are listening, but it's pretty straightforward. Most calculators these days can handle it, and then you just punch it in, and then whatever answer you get, write down. So that is it for trigonometric identities. That's it for the trigonometric functions, sine, cos, and tan. I think we have been able to give a basic concept and understanding of how these functions come about, how they work, and be able to going into the future, be able to see and understand. Okay, I can do this here, I cannot do this here. So that is what it entails. So next thing we're going to be moving on now to are the conic sections. The conic sections. So yeah, welcome back. So the next thing we're going to be looking at now is the conic section, right? So what are these conic sections? What are we talking about now? What is a section, first of all? I think it's important we give definitions to these terms so that it's easy for you to understand. So just imagine you have a cube of a block, right? A cube of block. Now, if I bring a knife and come to the middle of that block and then cut it from top to bottom, right? I have just made what? A section. I have just made a section. I have opened up that block of, assuming it's wood, right? I've opened it up. Now, the place where the knife passed through must have formed the shape. Now, that shape is obviously going to be dependent on the material, surface area, and what goes into the printing and the production, right? However, we're not looking at cubes here now. We're now looking at conic sections, so sections for cones, right? And now conic sections, how are they formed? They are formed by the intersection of a plane, which is the knife in the analogy I used earlier, with a double napped cone, right? So that's just the type of cone that we're using, a double napped one, something that has a base underneath and it's round, right? It's round. So we have 4 basic conic sections we're looking at. We have the circle, the parabola, the ellipse, and the hyperbola. Now, how are they formed? So for the circle, so we have a very good diagram which explains how these things come about. So for the circle, let's again use the knife analogy. You have the cone, and then you make your knives to be parallel to the floor, and then you just cut across, and that gives you a circle. Now for the ellipse, of course, you change your angle and put it at a different angle, and then cut across, right? So that's your ellipse. Now for the fact that for the hyperbola and the parabola, of course, they are also rules. So the hyperbola is cut along the axis of the cone, and then the parabola is cut along the side. So it's important to be able to discern and understand these things because they'll be important going forward in applying the formulas. So the first two equations we're going to be looking at are the equations for the circle and the parabola. Now, when I say equations, it just means what you use to represent them. So like it's formal, so but then it's important to be able to know the equations for each of these sections. Right, so for the circle, the formula is given as below. So we have x minus h all squared plus y minus k all squared plus r squared. Now these terms, of course, we have plenty letters, and when we start dealing with letters, but then it's necessary because we're looking at a general form, right? We're not just looking at one particular case study. It's a general form, right? And so this is general form that is used to represent the circle equation. So of course, the terms are defined. So h is our center, and then k is also our center. And then, right, so for the circle formula, the variables, we have h and k. But on your Cartesian plane, you have the x coordinate and the y coordinate. So this is like a representation of where the center is on the x coordinate and the y coordinate. So we have that, and then we have our radius, right, which is our r. So a and b is provided for. Sorry, x and y. H and k is not provided for because those are the unknowns, and then they mark the center, and then b as well. So an example just to illustrate what it will look like if you are going to go to one. What it will look like is x minus 2 plus y plus 1 all squared equals to 9. So from this equation now, from this general form of equation, we know that our h and our k form the center of this circle, right? So, and then the general equation has x minus h. So this is x minus 2. So we know that h is 2. The general equation has y minus k, and this is y plus 1. So we know that k minus 1. So it's important to be able to know and understand this story. So then the parabola also, each of these conic sections, but based on the fact that they have been taught differently, have their own differing equations, right? For the parabola, the formula is given as follows: y equals ax squared plus bx plus c, right? So it's important that you know and understand what these terms stand for, right? So for when we're talking about the parabola, we're not using a center in the case because it's not exactly a uniform shape. So we're talking about the vertex, right? And so the vertex for the parabola is this particular point, right? This particular point. Of course, it has its own coordinates on the x and the y axis as well. So x minus h all squared equals to 4a into y minus k. So you have to call this separately and then call this separately. Right, so these are the equations for the circle and the parabola. And likewise, we have equations for the ellipse and hyperbola. So it's important to be able to identify what each section is, because I think more often than not, the highest they can give you in an exam or something to solve is they represent these conic equations and tell you, okay, this is the equation of a circle. Find the center or find the radius. So in order to be able to do that, you're going to have to know what the general form looks like, know what all the terms stand for, and then you now find the information they are looking at and you are able to provide it to them. So it's pretty straightforward. It just involves knowing all the formulas and all the representations, right? So for the h and k in the parabola equation, represent the point on the vertex. For the ellipse equation, of course, there's also its own formula as well. So this is written right here and have a hyperbolic formula. Right, so the ellipse equation has its own kings, and then the hyperbola equation as well. So it's important to be able to know these things, have them at the back of your mind so that you're able to identify them when the occasion or the need arises. So in summary, we've been able to look at trigonometric graphs. So we've sketched and analyzed trig function graphs. We looked at the inverse trig functions. Now, before I continue. One important thing to note when you're doing inverse trig functions is because like I said, we're going to be given the so it's not inverse trig functions, it's in trigonometric functions themselves. So I mentioned that the sine function, the cos function, they are all cyclical, right? So they go back and repeat at the same point. So for example, it's important to note that when you are given a big angle or a big degree, that if you're using your Fofigo table, for example, you cannot find your Fofigo table, because you know that the period of the sine function is 2 pi and the period of the cos function is also 2 pi. If it's something that is greater than 180, you know that the period is 2 pi. So it means that when you get to 180, you start again, right? The function starts again as shown in this graph and does the same movement. So you can easily just subtract 180 from whatever that your angle is, and then that answer you get, you now work with it. It is obvious that your answer will be the same because the function is cyclical. So that point plus 180, that other point for 180, they will all keep giving you the same answer, right? Because the sine function is cyclical, it repeats, and you repeat after every 180 degrees. This is why I chose that you should add 180, right? So you see that it repeats after every 180 degrees, and so that's why we have that the period is 2 pi in radians, right? So that's another important thing to be able to note and figure out for yourself. And then so we looked at inverse trig function, we looked at conic sections, and then we looked at the general properties of each code. So yeah, it's a pretty short class today because it's a continuation of the leftover from last week when we kicked off. So it's just trying to wrap up what we've already started. So there isn't a lot of things to talk about, but then for those of you on the call, for those of you that have been following, if there are any on the call, if you have any questions, if you have any things that you want to ask, and then you can also pop up questions, and then feel free to help me. I'll be happy to glad to answer your questions. So if there are no questions, I think we've come to the end of today's lecture series on trigonometric functions. So we have a few practice questions here that you can simply just try out on your own. So the first one is to sketch the function of sine x from 0 to 2 pi. Then solve the trig function, so that's cos theta is equal to 0.5. So little hint, this will involve doing an inverse function, because now you don't have the degree, you don't have the angle, but you have the result, you have the output. So you normally apply the inverse trig function, able to find the degree. Then write the circle equation, giving the center as 1,2 and even the radius as 4, and then identify what conic section this is. Right, so they give you the equation and then identify what conic section it is.